to the like you for the exam through the chapter 1 to chapter 3. It will be helpful.
I can answer specific questions.
Okay.
I mean, you should go through all the Measure 2 material to review. Like if you're wondering how to review, I mean, just we can go through it section by section. What did we need to know from section 1.2? Element of, subset of, proper subset of, cross products. Okay, those were like the main set things that we learned. In section 2.1, we learned about statement forms, and we learned to evaluate the AND operator, the OR operator, and the NOT operator, right? And we learned how to make simple truth tables, for statement forms. And I can't remember if logic, I'll put section 2.1 and 2.2 together. Negating statements. And we learned De Morgan's laws. And then we learned about conditional statements. And we learned how to negate them. Right? And then in 2.3, oh yeah, we learned to make a truth table. A truth table to see if two statement forms are logically equivalent. We learned about tautologies and contradictions. They're either always true or always false. And we learned about argument forms. And we had some valid ones and some invalid ones. And we have the algorithm for determining argument validity. Conditional statements. Oh, but we also had the biconditionals. Remember the biconditional P if and only if Q? And it had a truth table P, Q, P if and only if Q. And if P is true, true, false, false, and Q is true, false, true, false. Remember how to evaluate the biconditional? P if and only if Q. Like I'm assuming that you know I'm assuming you know how to evaluate if P then Q. Can we feel like, do you remember how to evaluate if P then Q? How about in row 1? P is the hypothesis. Q is the conclusion. So what's the truth value of if P then Q when the hypothesis is true and the conclusion is true? Sunita, are you there?
Yes.
So do you know how to fill in the truth table for if P then Q?
Yes.
So how do you do it? What's in row 1?
If P is true, then the Q is be true. It's true.
Okay, what about row 2?
It's true. Oh, it's false.
Good. What about row 3?
It's true.
What about row 4?
It's true.
Good. Do you remember how to evaluate the biconditional? P if and only if Q?
It's like P imply Q and Q imply P, right?
That's right. But the
Mhm.
quick way to do it is to realize that the biconditional is true when P and Q have the same truth value. If they're both true, the biconditional is true. If they're
Okay.
both false, the biconditional is true. If P and Q have opposite truth values, then the biconditional is false.
Okay. So,
Okay? And then
mhm.
you have to be able to use the algorithm for determining argument validity and figure out if an argument form is valid, right?
Mhm.
And in 2.4, we learned about circuits and drawing them from the Boolean expression. And we also learned about making the IO table from
Mhm.
the Boolean expression when it was in disjunctive normal form.
Yeah, it's on that.
Remember that? We can just read off the IO table if it's in disjunctive normal, if the Boolean expression is in disjunctive normal form. And in 2.5, we learned about adders, right? The half adder adds 2 binary digits, P plus Q, and the full adder adds 3 binary digits, P plus Q plus R. And we learned how to construct a circuit to add, longer numbers. And then in chapter 3, we learned about quantifiers, for all X and D, P of X, but we learned how to negate that. The negation is there exists an X and D such that P of X fails, right? That was the universal quantifier. And the existential quantifier, there exists an X and D such that something happens, some property holds P of X, but when we negate it, it flips it to for all X and D, that property fails, right? Then we looked at multiply quantified statements. And we used our Tarski world as a way to practice negating and evaluating, understanding when a multiply quantified statement is true. That's kind of the short list of topics, but I think that's most of them. So if you have a particular topic that you're struggling with, we could work on it. But this is the kind of thing that it's helpful for you to go through, just kind of review the WebAssign. You can look at the answers, of the ones that you finished and all the measure to material and all the quizzes. Have you had a chance to work through all the measure to worksheets and special homeworks and the practice quiz? Here, I'm going to share my screen. Let's see if I can bring up.
Quick question,
Yeah,
but I don't know, practice quiz, the one that was just supposed to, the one you just posted
yeah,
for
measure.
the first part of the question.
Then this practice quiz on circuits.
Yes, I got a question on part A. Yes, are they not, I don't know, not output always on the left?
Output's always on the left. We always draw our circuits from, did I say output on the left? Excuse me, other left. The output's always on the right. My bad. I get right and left mixed up, but we read from right to left. So the
Yes, what I'm saying is,
inputs come in on the right and then they exit on the left.
what I'm saying is there are like three ends, uh, three ors. I mean, not, and then there's an or,
Yeah,
which is basically the final output.
yeah. You can see because the AND gate can take several input wires. The AND gate can take more than two input wires because it's fan and K. So you can build one AND gate to bring for these wires, and then you can build one AND gate for those wires, and then you can build one AND gate for those wires. And once you have those AND gates, those three gates built, each one of those has an output wire, and you can OR those output wires together. Let's look at the solution.
Yes, maybe the solution will help clarify, I mean, something my question a little bit.
So,
Yes, what I'm saying is they not output. Are they always on the left or the end?
well, if it's in disjunctive normal form, it is. This particular expression is in disjunctive normal form. In other words, there's a complete description of the input wires here because we know that the P wire is hot and the Q wire is hot and the R wire is cold. And then inside this parentheses, there's a complete description of the input. It tells us P is hot and Q is cold and R is cold. And there's a complete description of the input wires inside this third parentheses. It tells us P is cold and Q is hot and R is cold. You see, and then those are ORed together. So when the expression is in this special kind of form, this is called disjunctive normal form, then the NOT gates will always line up first, then the AND gates, and then the OR gate. And this is the special thing about disjunctive normal form, is that it makes it kind of easy to build a circuit. And it also tells us exactly which outputs will be hot because these expressions 1, 2, and 3 inside the parentheses completely describe when we expect to have hot output. We want to have hot output if P was hot and Q was hot and R was cold, or if P was hot and Q was cold and R was cold, or if P was cold and Q was hot and R was cold. You see, so when it's in disjunctive normal form, the reason it's called a normal form is two things. One, you can always put any Boolean expression into normal form, and so it's universal, and it's also very useful. And the utility is that it makes it easy to draw the circuit because, like you said, the NOT gates always are to the left of the AND gates, and the AND gates are always to the left of the OR gate. But it's also very useful because we can just read directly from the normal form to the rows that would have hot output, you see. The row that where P and Q are hot and R is cold is actually row 2 here. See, it gets a 1. It gets a hot output. The row where P is hot and Q and R are cold is row 4. I'm just labeling this as expression 2, but it's row 4 where P is hot and Q and R are both cold. See what I mean?
Yes.
And then the third expression is actually associated with row 6 because P is hot P is cold and Q is hot and R is cold. And those are the three rows in the IO table that get hot output. They get the ones. Because it's exactly this expression that describes when we want the circuit to output a hot wire. In other words, we say the circuit lights up because there's usually a little light bulb as a test to see if there's hot output. So we only want ones in those rows that are described by these expressions inside parentheses. That's what I mean by these parentheses give us a complete description of the input state. You know, there's a whole row that's associated with P being hot and Q being hot and R being cold, namely this row 2 here. Does that make sense?
Yes.
So disjunctive normal form just makes it super easy. Now you can be given an expression and you
Excuse me.
were,
Oh, excuse me,
you
Professor.
were, go
I'm
ahead,
sorry.
go ahead.
I had a question about the table that you just showed us. For the input-output table, we use the standard form to arrange our ones and O's, and then we look for the row that matches the expressions in our Boolean expression,
That's exactly right.
which is why you have 3 rows assigned Boolean expressions. And do we have to solve all of the rows or just for the Boolean expressions?
You have to put O's in the other rows.
Oh,
Every,
I see.
every row in the output table will have a 1 or an O. These Boolean expressions tell us exactly when there's going to be a 1, because this expression basically tells us when we want the circuit to give a hot output. We don't bother to write when we want a cold output. We just understand that what we write is when we want a hot output. And then the understanding is in all other cases, the output is cold.
I see.
And so I hope I answered your question. So this disjunctive normal form is super, super nice. Oh, I forgot my E. It's practic quiz instead of practice quiz. But anyway, did that answer your questions, Darius?
Yes.
Good. So there's all kinds of good stuff, you know. There's all kinds of, good stuff. This due later, that was a big problem that was given at the end of class, and then the solutions are in the office hour notes. So, we can go to office hour notes. And I think it's here that, that there was an argument. But I think also, yeah, this was a worksheet for binary addition, a different one, and then here's that great big problem. And I think Nura, you helped me work through this one night in office hours where we constructed this huge circuit using adders and half adders to add up these numbers. But here are the solutions to the other worksheet. I mean, there are a bunch of solutions here. Quiz 3 solution is here. A lot of solutions appeared. Like quiz 3. Solutions in the office hour notes from that same day, This was the argument, valid or invalid. Okay. So there's all kinds of good stuff. I think the quiz 2, the solutions are right there. And quiz 1, the solutions are right there. all kinds of good stuff. There was a whole review worksheet just for sections 2.1 to 2.3. There were a whole bunch of problems here, and the solutions are there. With explanations, another argument validity kind of problem. There's just lots and lots of material. So if you've been keeping up with this measure two material, the way that you were supposed to do, then you've gotten tons of practice. So if you're feeling shaky on anything, go to the measure two material, and work through some of these worksheets and special homeworks that you haven't had a chance to work through if you're feeling shaky on anything. Other questions, specific questions? So much stuff. Fluency, I don't know if you know what I mean when I say fluency, but fluency means not only do you understand the concepts, but you've practiced enough that you can do the work fairly quickly is going to be quite important on the test. We've covered a lot of material, so you need to be comfortable and not have to sit and think for a really long time on any particular problem. If you have to sit and think for a really long time, you're going to be in trouble.
I had a question about the quantified statements when there is a conditional or for every
Uh-huh.
in them.
Uh-huh.
When we start to negate those sentences, and for example, in the homework, there was a statement and it was added to another statement that was a conditional.
Okay, do you want to tell me which WebAssign homework that was in so that we can go together and look at that?
Yes. It was section 3.3.
Uh-huh. All right. I'm going to share my screen and we can view this as a student.
It was number 15.
All right. So section 3.3. Number 15. And that's the Tarski world. Okay. So we've got this Tarski world, and it says, is this the statement that you're looking at?
My question was more about the use of parentheses in the formal logical notation,
Okay.
especially for when we're negating.
So, okay. So were you able to figure out the correct parentheses for
I,
the original statement? It says there
I,
is, go ahead.
I'm sorry. Oh, no, no, I was just going to say, I translated the original sentence into formal notation, but I didn't add, I
The
added one set of parentheses.
parentheses, uh-huh. Well, you can always imagine another set. You just want to make sure you put it in the right place. Well, let me ask you this. What's the first quantifier for this statement? Is it
E-
universal or existential?
Existential.
So when we look for the expression that expresses the given statement, it's either going to be this one or this one or this one or this one. So we got it down to four, okay, because there exists this first. So there exists a triangle. So we want to say there exists an X that's a triangle. So they all say that, okay? Such that for every circle Y, X is above Y. So, such that means with the property that. In other words, X is a triangle and X has a property about every circle. So this first one says there exists a triangle, an X, it's a triangle, and for every Y, if it's a circle, something happens. The second one says there exists an X that's a triangle, or for every Y, if Y is a circle, something happens. This one says there exists a triangle X, or for every circle, something happens. And this last one says there exists a triangle X, and for every circle Y, something happens. So do you think it's going to be the and for every circle or for every circle?
The and.
Yeah, so we're down to two now. It's either this one, that there exists a triangle X, and for every circle Y, something happens, or this one, there exists a triangle X, and for every circle Y, something happens. So we're down to these two. Finally, we have to say, it says X, which is the triangle, has to be above Y. So here in this one, it says for all circle Y, Y is above X. That's what above XY means, is that Y is above X. Where this one, it says there is a triangle X, and for every circle Y, X is above Y. So which one do you think it is?
The last one.
It is. It's the last one. But it's sort of a process of elimination. Now, once we figured out that that's the correct original, now we have to work the hard work of negating that. So a bunch of stuff is going on, right? We have a there exists, we have an and then we have a compound if then. So it's a combination of De Morgan's laws, because we're going to flip the there exists. That's not De Morgan's. We're going to flip the there exists to what?
Two for every.
So it's either going to be this one, this one, this one, or this one. Okay, great. So we've got four that it could be. But now De Morgan's law says we have to negate this and statement. So what happens when we negate an and statement in De Morgan's?
It becomes an or.
So we know it's either this one because it's got a for all and an or this one because it's got a for all and an or this one, it's got a for all and an or this one. So basically there's actually all of the for alls have or, don't they? Okay, so it didn't help us much. Now, there's more that happens with De Morgan's. When we apply the negation to all this predicate, not only does this and flip to an or, what happens to triangle X, this component?
That gets negated.
It
But
does. But it's negated here with an or. It's negated in this one with an or. It's negated here with an or, and it's negated here with an or. So that's still not helping us. But we also have to negate this component. So we have to negate the for all and then an if then.
I have a question.
Yeah,
The for all statement, that is the hypothesis of the conditional.
it's the quantifier of the conditional. The for all is the quantifier.
But the for all circle,
Applies to the for
the
all
condition.
is being the condition on the for all is that we're really only interested in circles. But for all Y, if it's a circle, then we want X to be above Y. So, but again, we have to, because this is De Morgan's law working on this and statement, we have to negate this entire component. So we use the rule for negating a for all. It's going to flip it to there exists, but there's still a bunch of choices here. Then we have to remember how to negate an if-then statement. Because we're going to.
Yes. Oh,
So what
sorry.
is
I'm
it?
sorry.
Yeah, no, go ahead. So what's the negation of if circle Y, then above XY?
We leave we leave circle Y because it's a negation, and we leave the hypothesis in a negation.
That's right. We leave the hypothesis circle Y. And then and the if then becomes an and, which all of these choices are. And then we have to negate above XY. So how do we negate above XY?
We add a not
Yeah,
symbol
we
to it.
simply add a not. So now we're down to two. It's either this one for all X, not triangle X, or there exists a Y that is a circle and X is not above Y, or this one, and it is down to the parentheses. Oh, it's not, no, the parentheses are the same. It's a down to whether we want X to be above Y or Y to be above X.
I think it's the top one. We
It
want X to
is.
be above Y.
Yep, it sure is.
I had one more question.
Sure.
In your explanation just now, you maybe I misinterpreted, but did you express for every Y and circle Y? Are those two different components?
That is such a great question because we got a lot going on here. All right, so for the for this and operator, there are two components for this and, okay? Do you see in the original? One component is X is a triangle X. On the other side of that and, I'll try to pick up the whole thing. The other side of the and is this entire component, which is a quantified compound statement itself. It is a component that has components. It has a hypothesis, it has a conclusion, and it has a quantifier. So this is a very complicated component. Oh, I didn't want to grab that parenthesis. This whole thing right there is the other component of this and operator. Does that make sense?
Yes.
And indeed, we have to negate this entire monster. But we know how to negate an if-then statement. If P, then Q. We keep P, change the if-then to and negate Q. Since it was explicitly quantified, we know that flips to there exists. We keep the hypothesis, circle Y. There exists applies to all of this. There is a Y that's a circle and X is not above Y because we have to negate above XY. The negation of above XY is not above XY. It isn't not above YX, right? It isn't, not above YX. And it isn't below YX. They even gave you two ways that this was wrong, didn't they? Because below YX fails because the negation of above isn't below, and we don't switch the X and the Y, do we? And they did both. So it turns out to be this one, I believe. And that's a really good hard problem.
Thank you.
You're welcome.
Okay, so while we are here, can you review two question two?
Question 2 in section 3.3.
Yes.
Okay.
Yes, I'm a little confused on the
Okay.
on yes, on in the table, and what are we supposed to like? Are
Okay.
we
Well,
like
let's take a look at what the statement says, and that will help you understand why we need a table at all. What's the first quantifier in this statement?
like for every square x?
Yeah, right. And so it means we have to look at each square x one by one. And for each one of those, we have to find a circle y that exists such that x and y have different colors and y is above x. See what I mean? So for
Yes.
each square, we have to find a corresponding circle that satisfies that x and y are different colors, but the circle y has to be above x, okay? So the
Okay.
statement says no matter which square you might be given, you will be able to find a what?
A circle,
A circle that has
a different
a different color from the
from the square.
square, and still talking about the circle. The circle has to have a different color from the square and that lies
Above
above the,
square.
that's right, because we want y, which is the circle, to be above x. So they give us the list of squares, E, G, H, and J. So here's square E, G, H, and J. There are four of them. Thank goodness there aren't more than four. And so one by one, we have to look for a circle, make it a little smaller so we can see everything, that is a different color from the square that we're looking at, and the circle has to lie above the square. So for square E, for example, all right, let's do square E first. There's square E. Can you find a circle that's a different color from the square and that circle Y lies above square E? And there might be more than one that'll work.
Oh, for that, I cannot have B for that.
Yeah, B works because B is definitely a circle that's a different color. And is it above E? And of course, yes, it is. All right, what about for square G? Here's square G. Would you be able to use circle B for square G?
Mm, no, I didn't. No, I don't think so because
That's
isn't
right.
it on the left?
That doesn't matter. You see, oh, you're thinking above means good. I'm so glad we're having this discussion. Listen, see where E is? B is
Yes.
not the only object that's above E. C is above E. D is above E. A is above E.
Okay.
Above means in a row that is above the row in which E lies. It doesn't have to be in the same column to be above.
Okay.
Does that make sense?
Yes.
Like if you look at I and J, all the other objects are above I and J. They don't have to be like directly above, like D and G. A, B, C, D, E, F, G, and H are all above I and they're all above J as well. See what I mean?
Yes.
Same with left of and right of. Obviously, C, circle C is to the right of B. but actually square H is also to the right of circle B. It doesn't have to be in the same row to be right of. It just has to be in a column that is to the right of the column in which B resides. Got it?
Yes.
Great. So for square G now, we're looking for a circle Y that is a different color from square G and is above square G, but B wouldn't work because why would B circle B not work for G?
Because circle B is already associated with P.
Nope, that's not why. We
It's like
could have used
Y.
A for E and we could use A for G, but somebody else was speaking up.
It's the same color. GA.
Yeah, yeah, it has to be a
Oh,
different
yes, yes.
color.
I wasn't
Yeah.
paying attention, but
Oh,
color.
you see what I mean? Yeah, so actually A could work for both G and E, okay? You could have put A here and it would be fine. And you can use A for G as well. So different X's might have different partners Y, but they don't have to, but they can because the for all for each, I like to think of it as for each square, there is a corresponding circle Y, but some squares might share the same Y. It's okay. It's quite different when the there exists comes first. So do you got it? Do you think you can finish it now?
Yes.
Great. Other questions? Anybody have other questions on 3.3 while we're here?
I had another question.
Go ahead.
It's for number 3.F.
3.F.
Yeah, question 3, part F.
Oh, thank you. Question 3, part F. Oh, I love this one. This is when they go to the cafeteria. All right, so let's see. Let me just take a look. Uta gets a green salad, spaghetti, pie, and milk. Tim gets a fruit salad, fish, pie, cake, milk, and coffee. Okay, all right. All right, so part F. There exists, oh, I guess we have stations, right? The salad station, the main course station, the dessert station, and the beverage station, right? Is that what you gather from that?
Yes.
Okay, so part F. Can you read it for me?
There exists a station Z
Uh-huh.
such that for every student S and for every student S, there exists an item I such that S chose I from Z.
You want to try to put that into your own words?
I'll try. There is a station. Okay, there is a station Z that for every student, an item was chosen such that every every student chose an item from the station.
Yeah, it means, there's at least one of these stations that every student picked something from. Like either everybody got a salad, or everybody got a main course, or everybody got a dessert. Doesn't have to be the same one, but it's saying each student there is at least one station that every student picks something from, right? And so is there one? Did everybody pick well, definitely not salad, right? Because somebody didn't pick a salad. Who didn't pick a salad? Ewan,
UN?
Ewan, yeah, he didn't pick a salad. How about the main course? Did everybody get a main course?
Yes.
In fact, Ewan got two. So like that's one. Everybody got a main course. What about desserts? Did everybody get a dessert?
Yeah.
Oh yeah, so there's that one
Yeah.
too. You could pick. And what about beverages? Did everybody get a drink?
Beverages too.
Yeah, so in fact, there are three, but that means there exists at least one station that every student got something from. So yeah, so it says, haha, but it's a little tricky. It's a little tricky, isn't it?
Yeah, I was able, so I got confused on how it was written, but there only needs to be one station that all of the students chose any one item from.
Yeah, it's really weird. It's really weird. It is definitely true that every student chose a main course, every student chose a dessert, and every student chose a beverage. I mean, that's definitely true. Let's read what that second one says. That second one is looking weird. Although some students didn't choose a food from some of the stations, there existed an option for them to choose from. That just doesn't make sense. It's got to be the first one. I mean, we've said more than we need. You see, it's true, and they've kind of done overkill. It would have been enough to say every student chose a main course, that would have been enough. But in fact, every student chose a main course, every student chose a dessert, and every student chose a beverage. Those are all true. And that means not only was there just one station, Z, there were actually three stations, Z, from which every student chose an item, right?
Right.
It's very confusing. But the only reason I'm saying it's got to be the first one is because the second one just doesn't make sense, There existed an option for them to choose from. We don't even know what option I mean, are they talking about food option? Are they talking about station option? You know what I mean? Like that's sort of ambiguous. Existed an
Ah,
option for them to choose from. You see what I mean? Like every station has an option. So I think that the first one is the correct reason, but it does seem like overkill. Because we need at least one. We need at least one station that every student chose an item from. But the
I
first
see.
see what
Okay.
I mean? Yeah, they overkilled it.
Okay. But as long as there existed one station, then it would have been true.
That's right. And I think the reason the authors went ahead and listed all three of the stations is they weren't really sure if whoever was looking at the problem, if they'd catch them all, You know what I mean? Like, I'm pretty sure this is right. I mean, it's certainly a true statement, and it addresses the issue. It over addresses the issue. But I like this problem. I think it's kind of interesting.
Thank you.
You're welcome. Other questions? Anybody else have questions on the
Yeah.
WebAssign 3.3?
Can you look the question 4?
Question 4. All right, here we have a specific finite set D, which is actually the same as set E. And we have to write the negations for each of the following statements and determine which is true, the statement or its negation, right? So was was there a particular part you were having trouble with, or do you want to just start with A and talk about it?
I think yeah, I can start it on A because I was doing the 3.2 and then it was like similar question and I left that.
Yeah, now we have two quantifiers, right? That's the big difference. We have a for all x and d, there exists a y in E such that x plus y equals 1, right? So when we negate that, what happens to the for all x and d? What happens to for all in the negation?
They exist. They exist.
That's right, there exists an x, and you stick with the x. We don't change the domain and we don't change the variable. Okay, now we're bringing the negation through. There exists an x and e. Oh, excuse me, there exists a y and e, right? I'm going to make this bigger. So when we negate there exists a y and e, what happens?
Over for all x,
X or y?
it's y.
It is y, because we don't change the variable and we don't change the domain. Such that, and now we have to negate this predicate. How do we negate x plus y equals 1?
It's not equal.
That's exactly right. So that is a negation. So now we got to figure out if the given statement is true or the negation is true. So let's just look at the original statement. For each x in this set right here, does there exist a corresponding y in this set right here such that x plus y will equal 1? Well, let's just start checking. When x is -2, is there a value y in here such that -2 plus y equals 1? What would we have to add to -2? If x was -2, so let's say x is -2, right? That's the first of the each x and d. What would we have to add to -2 to get 1?
Oops, sorry.
What
Wouldn't
would
I'm
it
sorry,
be
y
like
that's
the
me.
positive?
what would y have to be? If x was -2, what would y have to be so that -2 plus y equals 1?
Like the positive 2?
That would equal 0.
Oh, no, the 1.
Yeah, we have to get 1 in this one. Well, just solve for y. If x is -2, solve for y. What would y have to be, folks? When x is -2. Put a -2 in for x and solve for y. What y would you have to get? Come on, folks, add 2 to both sides. All right, hang on. This calls for paper. X plus y has to equal 1. You agree? Now, x is -2. We're trying to check out if there's a y. Remember, D and E are the same set. All right, so if x is -2, we put -2 in for it. So -2 plus y has to equal 1. So what y would work? We'll solve for y. How do we solve for y? Add 2 to both sides. Y would have to equal 3. Isn't that true? Wouldn't you have to have y be positive and larger than -2 to get a sum of 1? There is no 3 in there. You would need 3 because -2 plus 3 is equal to 1. We don't have 3 available. See what I'm saying? So it fails right off the bat. It fails for the very first x. The very first x we would check would be x equals -2. There is not a y in there. And so, in fact, the negation is true. There exists an x in D, namely x equals -2, such that for every y in E, doesn't matter which one of these you take for y, no matter which one you take, and -2 plus that y is not 1. So the negation is true. Does that make sense?
Yes.
All right. So you just have to be able to solve a little simple algebra, but also understand that x and y are both coming from the same set. And this particular statement had to be true for every x in D. And so we check each x one by one. kind of the same way that we checked each square one by one in that Tarski world to look for a circle that was above the square and a different color. Well, for every X in this set, we're looking for a Y that is big enough to make X plus Y equal 1 when X is negative, and small enough to make X plus Y equal 1 if X was here. Like, try X equals 2. That might be easier. Is there any number in here that we could add to 2 and get 1? Oh, yeah, there is. We could add Y equal -1. That would work. I think it only fails for X equals -2, actually.
But that's enough, right? Because it's supposed to be for every X.
That's right.
So
And it was
if
nice
any
of,
X fails.
that's right. You're right, Nura. That's exactly the point. All it takes is one X for which it goes bad. What do I mean goes bad? There's a one value of X. There exists an X in D such that no matter which Y you check them all, for all of them, X plus Y fails to equal 1. That's right. And it was very kind of them to put the X that things go bad for first. Because we just kind of naturally start checking from the left. It's just sort of a natural thing to do. If you started checking X's from the right, you would have had to check all of them before you would have gotten to the X that satisfies the negation. Do we want to do the next one?
Yes, could we please look at number 5? Because it uses the entire set of real numbers. And
Okay, hang on. But Sunita, I wanted to ask, or Max and Joy, whoever asked for this one, was it you, Sunita? Did you want to look at B?
Yeah.
All right. All right, you help me. We're going to negate this statement. Okay, so what happens to the there existent X and D? We're negating it.
For all X,
Good. What happens to such that for all Y and E? What happens to that?
exists Y.
Great. Oh, there exists Y. Good. And
The
then what happens to the predicate X plus Y equals -Y?
2 minus 2 plus minus Y.
Just the equal to changes to not equal to.
Oh, not folio.
Okay, so now this one just says, the original is exist. Does there exist an X? Now, the thing about this is the existence comes first. We have to find an X that works for every single Y to make X plus Y equal to -Y. Holy cow. Could there be a single X that would work for every Y to make X plus Y equal to -Y? Well, let's just say we're going to try to play the game with X equals 0. Maybe that would work. But if you pick a Y, like Y equal 1, is 0 plus 1 going to equal -1? Nope. So 0 can't work. In fact, there is no X that can possibly work for every Y. Let's just take a look at Y. There exists an X in D such that for all Y in E, X plus Y equals -Y. Let's just take a look at, we can play with this predicate a little bit, all right? If we do a little algebra here, if we add Y to both sides, this means X equals -2Y, right? If you subtract a Y from both sides, it tells us that X has to be -2 times Y, but it has to work for all Y. Well, the minute you pick a Y, like say you pick Y equals 1, well, there is an X that works for Y equals 1, namely x equals -2. But we have to find a single x that works for all y. Well, y equals 1 has to have x equals -2. Y equals 0 cannot use the same x because x has to equal -2 times 0. See, here it worked because -2 equals -2 times 1. But if y is 0, the x would have to be 0. And this claims that there is a single x that would work for every y. It's impossible because here we're looking at two different y's and they require two different x's. There's just no way to find a single x that'll do the job for every y. So what that does is it makes us realize, gosh, the negation must be true. In other words, for every x in this set, we should be able to find at least one y in this same set for which x plus y is not equal to -y. And it's true, if you pick x equals -2, you can find a y so that x plus y is not equal to -y, right? You can pick x, you can find, you can pick y equal 2, right? That exists. And for x equals -2, x plus 2 is equal to 0, and that's not -2. But then you can check for x equals 1. Can you find a y so that -1 plus y isn't equal to -y? Sure. You can pick y equals 0. -1 plus 0 is 0. Oh, wait a minute. No, I can't pick 0. If x is -1, let's pick +1. -1 plus +1 is 0, and that's not equal to -1, which is -y, because we picked y equal 1. This one's a little tricky, but the negation is true on that one as well. What about this one? For every x in D, there's a y in E such that xy is greater than or equal to y. Let's try to just get the negation right. What happens to the for all x in D? Benita?
X
Exists in x. Good. Such that
the universal y.
for all y, such that, there exists an x in D. No, excuse me. There exists an x in D such that for all y and E, what happens?
Does
X,
not.
y,
It's
we want to negate greater than or equal to.
it's less than equal to.
Good. So either we got to check for every x, we got to find a y such that x times y is bigger than y. Oh gosh. So if we start with x equals -2, can we find a y so that x times y is bigger than y? But if we pick a -y, then -2 times -1 would be 2, and that's bigger than -1. So we found a y for x equals -2. Now we have to check x equals -1. Well, we could pick y equal -2 as y, right? And -1 times -2 is 2, and 2 is greater than or equal to -2. Okay, good. What about if x is 0? Can we find a y so that 0 is bigger than y? Sure, just pick a negative value for y, and the 0 times y will be 0, and that'll be bigger than the negative. What if x is positive? What if we pick x equals 1? Can we find a y so that x times y is bigger than y? Sure. Pick 2 for x. No, I mean, no, that won't work. If x is 1, what can we pick for y? Oh, pick y equal 1. Then 1 times 1 is bigger than or equal to 1. That works. What about if x is 2? Can we find a y so that 2 times y is bigger than y? Yeah, pick y equal 1. All right, so that was a pain, but that one's actually true. All right, enough of that. We're going to go on to the next one. I might think twice before I assign that one again. That one's a pain in the butt. I'll let you do the last one. You just have to go through and check. All right, Nuri, you wanted to look at this number 5, was it?
Yes.
I'm sorry.
Oh, yes. This was it. Yeah.
What's going on with it? What's the issue?
Um, the sets are too big to, so I don't know how to approach it. Oh,
Okay.
no, that's not it. No,
Um,
this is it.
well, I think, the numbers that are in red, they show up in red. That means they can be different for different people, okay? Like it generates a range of values. Is this it?
Yes, because there exists a real number, so they could be any real number.
X.
Wait a minute,
Oh,
I
no,
don't, there's another.
does yours say for every real number there exists a real number, or is yours different?
Mine says for every real number x, there exists a real number y such that the equation is true.
Okay.
And then there exists a real number x such that for every real number y, the equation is true.
All right. All right, this is the deal. All right, so let's take a look. It's an equation in 2 variables, and there are a couple of different ways to attack this. Um, this is the equation of a line. You can kind of understand that this is an equation of a line, or we can just look at it naively without knowing any geometry. And let's just ask ourselves, for each real number x, so let's just imagine you plug in any real number for x, like x equals 1, just any real number. Can you solve for the y to make that true?
Yes, because you can choose any number.
Yeah, I mean, if you choose any x, you plug it in, multiply it times 3, and subtract that from 8, and you can solve for the y, right?
Yes.
So certainly statement 1 is true. We can always solve for y once we plugged in a value for x. But now it says there exists a real number x such that for every real number y, the equation is true. That's not true, because if you pick one value for x, that determines what y has to be. Like once we plugged in a value for x, right, then we can figure out what 3 times that is. And that determines y, because y would be 8 minus 3 times that x. It can't work for every y. There's only one y that would work for a given x. See what I mean?
Oh, okay. Yeah, okay, I see. That makes sense.
Right? There's no way one value of x can generate all of the y's. Each x then is associated with a single y. So only statement 1 is true. But look at the next statement. You see, y plus x equals x plus y. That's a tautology. That's always true, no matter what x and y are. Now, that may or may not impact our decision. This says for every real number x, there exists a real number y that makes the equation true. Sure, if you put in x here and x here, they cancel. And you see what I mean? Like if you put in x equals 3 here and you put in x equals 3 here, you can subtract 3 from both sides and you're left with y equals y. Certainly, there's a real number y that makes that true. In fact, you can plug in x equals 3, and it doesn't matter what y is, the equation's always going to be true. Let me show you. This one, again, deserves a little bit of discussion. X plus y equals y plus x. Or maybe it says y plus x equals x plus y. Okay, it doesn't matter. Y plus x equals x plus y. The point is, if you pick x equals 3, okay, and we plug in 3 here and here, well, subtract 3 from both sides, the 3's go away, and you're left with y equal y. That's true for all y. That means there is a y for which it's true, and it's true for all y. Doesn't matter what y is always equal to y.
Can we look at some of the ones? There's a rather large, it looks like a perfect square formula. I'm not sure, but as it goes down, the equations become more complex.
Okay, so this is a perfect square. Okay, this is x minus y quantity squared. Okay. So if you factor this to x minus y times x minus y, and that is a perfect square. Can you see that?
Yeah.
All
Your
right.
camera shifted? I'm
Oh,
sorry.
no, I'm so glad that you told me that. 'Cause is that okay?
Yes, thank you.
Is it in focus?
Yes.
Okay. So this is, so this is equal to 0. All right. So listen, let's just think about what it takes for anything squared to equal 0. There's only one number whose square is 0. What number is that?
0.
Right. So this means that x minus y itself has to equal 0. Well, that means if x minus y has to equal 0, well, what does that tell us about the relationship between x and y? X has to
It's a,
equal y,
oh,
right? So this actually forces this. So now let's go back and look at what we're trying to say. I signed this one? I didn't mean to sign this one. I actually assigned this one. I apologize. Okay, but this actually can be just a little heads up about how your algebra is. All right, so this first statement says, for every x, there's a y that makes the equation true. Yes, because for every x, if you pick the y that's equal to x, it'll make this true. But the second statement says there's a single x that would work for every y. That's not true. Because the minute you pick an x, it's only going to work for a single y, namely the same y that it is equal to, that's equal to x. So only statement 1 is true. There's no single x that can work for all y to make that true. I mean, you could, if you don't even know factoring, just think, for every x, there is a y. So if you pick x equals 1, we're saying 1 squared minus 2 times 1 y plus y squared equals 0, right? So we're saying 1 minus 2y plus y squared equals 0. Well, it turns out, you can solve for y. It's y squared minus 2y plus 1 equals 0. This is x, y minus, it factors to y minus x. This y minus 1 times y minus 1 is equal to 0. I mean, you got to do a little algebra anyway. But the point is this product is equal to 0. Well, the only way a product is equal to 0 is if one or the other factors is equal to 0. So, I mean, you can see right away, this forces y minus 1 to equal 0. It forces y to equal 1, which was x. The point is, given an x, there's only one y that's going to work to make this equation true. If you pick a particular x, there's no way it can work for every single y to make the equation true.
I see.
And honestly, I kind of feel like I should apologize for even assigning this one. I think it slipped through my radar. It's not that many points, you know, in the big scale of things, but it does kind of give you a heads up about your algebra, you know, the strength of your algebra skills.
Quick
I
question.
do.
Yeah, Darius,
Does that mean that this part will not be on the test?
I'm not going to ask one where you have to factor a quadratic.
Okay.
Yeah, no, don't lose sleep over that. But you know, simpler ones like, you know, x plus y equals 1 or something like that, you know, we did, in fact, my initial examples, remember, when we did multiply quantified statements, we went over a whole bunch of little simple statements, right? They were even simpler than these, the statements in our notes, but they did have to do with a finite little set, you know? So that's fair game, but something simpler. Yeah, I'm gonna have to throw this one out for future semesters. I'm glad you pointed that one out. Other questions from this homework? See, this is a little easier. This is more like what we did in class, number 6, right? I mean, these are just kind of basic, simple facts about inverses. This one says for every non-zero real number R, there's a real number S such that the product is 1. Well, all you got to do is just think about some non-zero real numbers R. If you just kind of just think about it, for all R in the reals that's not 0, so subtract away 0, there exists an S that's in the reals minus the 0. Now, we didn't really talk about set subtraction, but that's what set subtraction is. Just take the 0 out of the reals such that RS equals 1. Well, let's just think about it. What if R was 3? What would be the S that we would need so that 3 times S would equal 1? What S would work?
We would use the reciprocal.
Yeah, 1/3. And so no matter what R is, you would just use R times 1 over R. That's your S. And since R is not 0, 1 over R is defined. So, you know, so there is always an S. For every R, there is an S. As long as R is not 0, there does exist a reciprocal 1 over R that can work as S. But so for A, it's true. For each R, there is an S that'll correspond. But the second part says that there's a single number R that'll work for all non-zero S to make this true. And that's simply not the case because the reciprocal of S is is R, is what you would take for R. So the same reciprocal would not work for different S's. So the first one is true, that given any real number, let's see, given any non-zero real number, a real number can be found so that the product of the two equals 1. Yeah, that's true. But there is no real number that's non-zero that would work for every real number, because that's what this says. This says that there is a real number whose product with every non-zero real number equals 1. Yeah, that there is a single real number that would work for every non-zero real number. Yeah, there simply isn't one. There is no such real number, because every real number has its own private reciprocal. So it's really trying to show you the difference between having the for all in front of the there exists versus having the there exists in front of the for all. They're very, very different statements. That's the point of those two. I kind of like that problem. That one's not so hard. Other questions?
Uh,
Don't get, buried in the details. Study your Tarski world, you know. Look at the Tarski worksheet. Finish that. Focus on the Tarski world questions. I like Tarski's world. That's why I gave you a handout on it. Sunita?
yes, can I look at the one more like time 3.2 question 6? Or I can share my screen.
Okay, hang on. Let's see, 3.2. Okay, let's see if I can get out of 3.1.
I have done like some of the A and E, but the other three is like
What problem number? 2?
the
No, which problem number?
B. And the question 6.
Yeah, I mean, it says no response because I've got it in student view, okay? So don't worry about that. All right, so here it says determine if the following statements are true, which are true and which are false. So the first statement says, can you read that statement?
Oh, X. Can you? Okay.
Can you see it? Is it big enough on the screen?
Yes.
Yes.
Do you want me to read it for you?
Okay.
You're breaking up. Can you see it?
Yes, I can see.
All right, it says for all X and D, and here's our set D. If X is odd, now do you know what the odd numbers are? Odd
No.
numbers are not divisible by 2, like 1, 3, 5, 7, -1, -3, -5. Those are the odd numbers, okay?
Mm.
If X is odd, then X is greater than 0. So we're going to look in D, and we're going to look for the odd numbers because the condition is that X is odd, right? So we look for when the condition is true. We always look for true hypothesis. All right, this is even, it's divisible by 2. This one's even, this one's even, this one's even. Okay, here's our first odd number, 1. Is 1 greater than 0? That's the conclusion that has to be satisfied. 1 is odd. Now we're checking. Is 1 greater than 0? Sure. So far, so good. Now we keep checking for more odds. 3 is the next odd number. 3 satisfies the hypothesis. It's odd. And yes, 3 is greater than 0. And then the next odd number is 23. It's odd, and it satisfies 23 is greater than 0. So the only odd numbers, which are 1, 3, and 23, all satisfy the conclusion. So the 3 numbers that satisfy the hypothesis, X is odd, there are only 3 of them. They all satisfy the conclusion because they're all greater than 0, namely 1, 3, and 23. So that's true. Does that make sense?
I get through that. The question B, C, and D, the E and also I got the true. I mean
Which one do you need?
the B, C, and D.
Now you tell me. Okay. So what does B say? It says we look at each X and D. What's the hypothesis? It's an if-then, right? It's an if-then. So the hypothesis is that X is less than 0. So what does it say? It says if X is less than 0, then X is even. Well, look at the numbers that are less than 0. Are they all even?
Yes.
So that's true. Now, it does say that if its statement is false, then you're going to give an example to show why it's false. So eventually we're going to come up with one that's false. So what does C say? It's an if-then, and it's universally quantified because all if-thens are. It says if X is even, then X is less than or equal to 0. Is it true that every even number is less than or equal to 0? Because that's the hypothesis is that X is even, okay? So we can look at all the even numbers one by one, and we have to check that the conclusion follows. And the conclusion is that X is less than or equal to 0. Well, that's true when X is negative 48, that's even, and it's less than or equal to 0. That's true for negative 14, that's even. It's less than or equal to 0. Negative 8 is even. It's less than or equal to 0. 0 is actually even because it's 2 times 0, and it's less than or equal to 0. But what about 16? Is 16 even?
Yeah.
So it satisfies the hypothesis. Is 16 less than or equal to 0?
It's greater.
It's
Yeah.
not less than or equal to 0. So this statement is not universally true for all even numbers because we found an even number in this set D, talking about elements of D. We found a number that satisfies the hypothesis, it's even, and it failed to satisfy that X is less than or equal to 0, right? So you could use X equals 16 or 26 or 32 or 36. Those are all the X's that serve to show that this statement right there is not universally true because they satisfy the hypothesis. They're even. 16, 26, 32, 36 are even. And they fail to satisfy that they're less than or equal to 0 because they're all positive. Does that make sense?
Yes.
Now, D talks about the ones digit being 2, then the tens digit is 3 or 4. So you have to know what the digits are. All right, so let me just remind you, and we've talked about this in class. In the number 48, the rightmost digit is called the ones digit, okay?
Yeah.
It represents
So
8
like
times 10. 8 times 1. But the 4 is the tens digit because it represents 4 times 10. Does that make sense? Sunita?
Yes. So I put the answer 32 and then tens digit.
Well, if the ones digit is 2, then the tens digit is 3 or 4. Well, let's just see. Yeah, 32 is the only number where the ones digit is 2 and the tens digit is 3 or 4. So that's a true statement.
With
What about that last statement?
the last one I get but 32. When I put 32, it's like incorrect.
All right. But here it said if the ones digit is 6, not 2. It's Wait a minute. What you said on part D or part E?
No, E, it was like confusion, but I put 36 there. But the D, I put 32, it is like incorrect.
Oh, but you're not supposed. It says, well, let's read the directions. It says determine which of the following statements are true and which are false. If the statement is true, you're just supposed to enter true. If the statement is false, enter a value of X that could be used to show that it's false. But you told me that D was true because, and it is true, because the only number that has a ones digit of 2 is 32, and its 10 digit is 3 or 4, because its 10 digit is 3. So you should have written true for D, not 32.
Oh, sorry.
You only put in a value of X to give as a counter example to show if the statement is false. So let's take a look at E. Is E true or false? If the ones digit is 6, then the tens digit is 1 or 2. Is that true?
I put true.
Really? Well, what about 36?
No, I put 36 there, and it is correct.
Because it's false, because here the ones digit is 6 and the tens digit is not 1 or 2, it's 3. So you're right. In E, you should put 36 because it's false. But on D, you should have written true because it's true.
So I put number there, that's why.
That's why, yeah. Because when you wrote the number, you were entering a value of X, so it thought that you thought it was false. So it is really important to carefully read directions. That's critical and key on all of mathematics, right? Other questions?
Quick question.
Yeah.
I don't know. Can I look out? Because I'm about to go to work.
What's that?
I'm about to go to work. Is it okay if I leave?
Of course. You can come and
Oh,
go. You can dip in and dip out of office hours. Don't ever feel obligated to stay longer than you can. Have a good night.
you too. So,
Thanks for playing. I'm going to pause the recording for just a minute. Excuse me. I know there's a lot of material, but I do think if you just work through the measure two material and, you keep in mind kind of these main ideas. I certainly can't test you on everything, right? But you want to be able to do the main things. And the quizzes, should help you, right? Give you an idea of the kinds of questions that I might ask. Any other questions? think I'm gonna call it a night then, folks, because I've got still a bunch of work to do, okay?
Thank you, Professor.
You're welcome. Thanks for coming and helping make it a good office hour.
Yes,
Thank you so
You're
much.
welcome. Have a good evening.
Have a good night.
Have a good
See
night.
you.
Thanks for asking questions, Sunita. Your questions are always good.
Yeah.
Yep.
Thank you. Mhm.